Okay, again, apologies. I'll post an update on Google Classroom as to what is going on, but the long and short of it is I've got an ankle slash foot injury. I should be at school on Monday. Here's hoping we'll sort something out, but we're going to keep moving on. I would encourage you, by all means, send me questions and problems that you have, and I will do what I can to answer them, because I'm at home. I just can't really go anywhere very easily. But I am in theory capable of sorting out problems from afar. So I understand that there were maybe some questions about how you could skip the first derivative test to figure out concavity. I will make a small separate video for that and post it, although that's totally an optional thing. So if you're down with figuring out whether something is a max min with using the first derivative test, then the expeditious way of using concavity to tell you is not necessary. So anyways, what we're going to do today is we're going to look at the actual graphing algorithm, and this is sort of the pinnacle of graphing abilities in high school. So graphing algorithm. And today, well, I have no, what, today's the 24th, I think. Is today the 24th? Yeah, today's the 24th, which means you guys are seeing this the 25th. So March 25th of 2022. Right. So, you know, if we kind of do a quick recap of what we know from before this class, and, you know, encompassing stuff that you know in grades 9, 10, 11, and advanced functions, you know, there are some important things. So we can get intercepts, right? And so intercepts, if we're thinking about the y-intercept, you know, you can just sub x equals 0 and solve, right? Because if you think about a graph, y-intercept is always along here, which means the x value has to be equal to 0. So if we want to solve for the y-intercept, we sub x equal to 0 and solve. Boom, there it is. If I want an x-intercept, really, you do it the other way around. We sub y equals 0 and solve. And for the exact same reason, right? Like along this line right here, all your y values are going to be 0. In practical terms, it really is, you know, we often just think about it as being, you know, because it is the roots of an equation. And so, you know, it's as simple as that. Alternatively, if it's a rational equation, that's the only time that it gets really complicated. If it's irrational, then it is the zeros of the numerator, which are still the roots of the equation, but I want to clarify and make sure that we're on top of that. So the zeros of the numerator. Right, so that's our intercepts. We got our y-intercept from x equals 0. We have our x-intercept from, you know, traditionally we just think about it as solving the equation, and you know, that's basically what it is. Yeah, there we go. So intercepts we can get like that. So those are important pieces. Asymptotes. Asymptotes come again in like two big flavors. There are horizontal asymptotes and vertical asymptotes. So I'm going to go vertical first. The vertical asymptotes, they come from the zeros of the denominator after any cancellations have occurred, right? So we're always going to greatest common factor our numerator and our denominator, and we're going to look for anything that's in common. We're going to cancel those out. So after any cancellations have occurred, and those cancellations, what they represent, and I'll even put that here, the cancellations are removable discontinuities, right? The holes, basically. Okay, so vertical, they come from the zeros of the denominator after any cancellations have occurred. The cancellations indicate removable discontinuities. And then the horizontal asymptotes, they come in, well, multiple flavors. If we look back a couple of years ago, I would say 3 flavors. This year, we kind of scaled it back to 2, but the reality is there's far more than that. But the horizontal asymptotes, they are dictated, and they only, for our purposes, we're going to say they only come from rational functions. And it all, the cases revolve around the degree of the numerator. So the degree of numerator versus the degree of the denominator. And I'm hopeful that you remember that. I'll kind of, give synopsis. So, and I'm going to call it case 1, 2, and 3. But there's nothing magical about it, just as long as you know what rational function leads to what, we're good. So I'm going to call it case 1, and that's where the numerator's degree, so the numerator's degree is, let's do it less than the denominator's degree. So an example of that would be, for instance, f of x equals, x squared plus blah, 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 it doesn't really matter, over x cubed plus blah, 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 blah. So the numerator's degree is 2, and the denominator's degree is 3, so the numerator is less than the denominator. I want to remind, I emphasize like this like crazy in my advanced functions class. I'm not sure Mr. D did in his. I'm guessing he probably did. Horizontal asymptotes are only really powerful for extreme values of x. So it's only really powerful way out to the left and way out to the right. So what I mean by that is, if I just draw a really quick set of axes here, a horizontal asymptote, you can, and a big difference between a horizontal and a vertical is that imagine that we had a horizontal asymptote, at whatever, 2. You can cross a horizontal asymptote, right? Like a function could go like this till our heart's content. There's no limit to how many times a horizontal asymptote could be crossed. But eventually we're going to, well, not for our purposes, eventually we're going to decide on, either being above the asymptote or below the asymptote, and it will get close from that. But it's important to realize that a vertical or a horizontal asymptote you can cross. Anyway, this example is really bad. This is going to be actually case 2's. Case 1, but getting back to what I was saying, given that it only has power like for really big values of x, like an x value of -100, or maybe -1,000 or -1,000,000, if you think about it, that it's only valuable for really, really big values of x, it should lead you to believe case 1, you should be able to figure out that the horizontal asymptote is going to be at y equals 0 for this one. I should have used a different color. That's going to be case 2 over there. And the reason it makes sense that it's going to be at 0 is because we're going to take a big number, 100, and we're going to square it, and that's big. But then we're going to, on the denominator, we're going to take it and we're going to cube it, right? So 100 squared over 100 cubed, that's going to be a small number. It's going to get close to 0. And if you think about 1,000 squared divided by 1,000 cubed, that's also going to get even smaller, right? So that gets really, really close to 0. All of these other terms become immaterial for really big values because they just don't, they don't weigh in as heavily. So case 1 is when the numerator is less than the denominator degree, and it's going to be a horizontal asymptote at 0. And so again, I did a garbage job on kind of including this one over here. So case 1 is going to look like color. Your function can kind of do whatever the heck it wants, but maybe it's ends up going like this and like this. All right, so this would be case 1, is that it's going to have a horizontal asymptote at y equals 0. Case 2, so case 1 is this guy. It's let's get rid of that. That's not the right spot. Case 1 is numerator is less than the denominator. Case 2 is the degree of the numerator is equal to the degree of the denominator, right? So it's going to look something like f at x equals, 2x cubed plus blah, 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 over, x cubed plus blah, 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 blah. They have the same degree. And again, if we take the argument that, we're going to put in some large value of x, these other smaller terms, they don't count very much. And the x cubed and the x cubed, well, they're essentially going to cancel one another out. They're going to divide out to be 1. And what you're left with is the ratio of the leading coefficients, which in this case is 2/1. So this one would have a horizontal asymptote at x equals 2. Look at that. I didn't even thought about it because there it is right there. And so it is always going to be, this is the ratio of the leading coefficients. Right? And this is all review of grade 12, but advanced functions, right? So this should not come as a mystery to anybody. And then the final case, which I'm only going to just touch on it briefly, because we didn't really do it because of time constraints. But case 3, and again, we're arbitrarily stopping at 3. There's no reason. There's an infinite number of cases. But case 3 is when the degree of the numerator is greater than the denominator. And we're going to say 1 greater, although there's no limit. So if we had f at x equals 7x cubed plus 5x squared plus blah blah blah, doesn't matter, and then over x squared plus 7x plus 5, well, the numerator is getting bigger faster because it's a cubic versus this one, but it's only 1 degree higher. So this one would be, it's a special name. It's called a slant or an oblique asymptote. Right, and so for our purposes, it would look something like, maybe we got a slant or oblique asymptote right there. And again, our function can dance through that as many times as it wants, but eventually it's gonna, the asymptote is gonna exert its influence, and we're gonna have to get closer and closer to that slant or oblique asymptote. As a reminder, I promise you I'm not going to give you one of these, but in theory I could. The way that you would find the equation of the slant asymptote is you would do long division, right? So you would take and you would put the numerator in here, and we would put the denominator out here. And what we would get up here is, this is the equation of the, the family of horizontal asymptote. Now, it's not horizontal because I called it oblique, but it's in that family. And so, you can see here that if it was only 1 degree higher, the result would be linear. Why I said that there's, only for 1 greater is because if this was 2 greater, the evaluated answer here, the horizontal asymptote, it would actually, if it was 2 degrees higher, it would actually be a parabolic asymptote, because it would have to get closer and closer to some x squared function. So these are the 2 that we're going to deal with. We're going to deal with case 1 and case 2. Case 3 is just there just so that you're aware that there's no reason. And case 4 would be parabolic, and case 5 would be, cubic and quintic and quartic and whatever. I've got those in the wrong order. But there's really no limit. The only people I can fathom even seeing that at university are going to be if you go into like pure math. Like, I don't even think that if you went into just math in general, you would have, maybe you'd see a little bit of it, but if you're going into engineering or physics, it's, it's probably not something you're going to see there either, but, it does exist. Okay, so advanced functions, has gotten us, or the combination of grades 9, 10, 11 and advanced functions. We're going to get our asymptotes, we're going to get our intercepts. We also know end behaviors. Generally speaking, if it's a polynomial function, we're going to know our end behaviors. right? Because we know whether it's odd versus even degree and a positive leading coefficient versus a negative leading coefficient, right? So we have, you know, if it's just a polynomial function, then we're good on end behaviors. We've got that. End behaviors and turning points, right? We know that typically speaking, the number of turning points is one fewer than what the degree of the function is. And again, these are for polynomial functions. Okay, so polynomial functions. Yeah, so, you know, we go a long ways when it comes to what we're capable of graphing already. What calculus is going to bring to the table is it's going to tell you your maxes and your mins. So it's going to be able to find the tops of peaks and valleys, and it's going to tell us where areas of increase and decrease are. And it's also going to talk to us about areas of concavity and potentially points of inflection. I'm going to just take a pause for a second. Okay, so yeah, so our combined graphing knowledge is pretty decent, pretty comprehensive. So I'm gonna put together the graphing algorithm, and we're gonna do some examples. How much room do I have here? Not very much. I'm gonna do page over a little bit here, yoink, like that. Okay, so here we go for our graphing algorithm. Okay, so graphing algorithm. All right, so the first step, we just call it framing the curve. Okay, so frame the curve. And it's sort of, you know, break out everything we know, to be honest, right? So, you know, within that, we are going to find, maybe I'll itemize it like this. I was going to say roots, but I'll just categorize this intercepts, and that way we know that it's both x and y, right? So we want the intercepts, x and y. We want asymptotes. So we want vertical and horizontal or slant. You know, those two walk together. You can, in high school, you will only have one vertical or one horizontal or slant. You can have as many verticals as you want, right? Because as many zeros out of the denominator as you care to have. It's feasible to have more than one horizontal asymptote, but not in high school. Right. And so we itemized how all of those things work. And then really, okay, so then we can also, you know, we can look at end behaviors. And that's more relevant for polynomial functions. If it's not polynomial, you'll sort of see how that works. Like, well, I mean, I guess that's the point, is that if it's either polynomial, and we're going to know that because of the degree of the function, or it's going to be rational and there's going to be a horizontal asymptote. So yeah, so the end behaviors is, you know, you can determine what the end behaviors are up here. And then, like, so that's, you know, that's prior knowledge, right? And then we're going to get into more of the new stuff, and we're just going to call them important points and behaviors, right? Behavior starts with a B. Behaviors. So important points are behaviors. So we're going to do, you know, set f prime at x equal to 0 to look for max mins. And then within that, then we're going to do our first derivative test. Derivative test in order to determine areas of increase and decrease, right? That's what the first derivative test tells us, in addition to where maxes and mins are. Increase, decrease areas, right? Areas. Good. And then, you know, so that's the first part. and then we're going to set f double prime at x equal to 0 to look for, by and large, we're looking for points of inflection there. And then we're going to do the second derivative test. And yeah, and then, you know, we're going to lay all of these details together on a graph, and we're going to have for ourselves, yeah, a really accurate graph. So what I'm going to do is I'm going to just pause this, and I'm going to save this page, and then I'll be right back with a new page. Okay, so we'll go with a fairly basic rational function. Yep. Okay, so what we want to do is we want to sketch the following. I want to sketch f at x is equal to 2x over, let's make it a teeny bit more complicated. I'm on my other laptop again, and it doesn't have my buttons mapped. Never mind. So imagine that we had the following. Yeah, so 2x times, I don't know, x plus 5 time over x squared minus 9 times x plus 5. Now, because I decided to include this chunk at the end, I normally wouldn't have given it to you like that. Like, you know, I would have probably offered it to you fully simplified in the numerator and the denominator, right? So I probably would have given it to you as, you know, 2x squared plus 10x over, and then it would be x cubed, and so then I guess it would be plus 5x squared minus 9x minus 45, right? So I would more likely have given it to you in that form. And I guess a step that you might want to add to your own algorithm there is fully factor the numerator and the denominator, right? So you would do that, and you'd be like, boom, boom, and that's what we've got, although it's not fully factored. So we go one step farther, and we'd be like, okay, it's 2x times x plus 5 over x plus 3 times x minus 3 times x plus 5. And hopefully the first thing that you would observe is that they have a common factor, right? So you divide through by that, and you have to make sure that you state your restriction. So x cannot be equal to -5. But what we do have is, therefore, we have a removable discontinuity at x equals -5, right? So there's going to be a hole in the function wherever -5 happens to be on our function, right? So good. And so then, you know, so that simplifies then to become, we're like, okay, good. Now we are just 2x over x plus 3 times x minus 3. And we're going to look for our intercepts, right? So our intercepts, it's kind of a boring one in that regard. So we're going to set for the x-intercepts, we would set 2x equal to 0 and solve. Well, you know, yay, that's x equals 0. So we've got an x-intercept at x equals 0. And I don't even think I really need to discuss the y-intercept, but the y-intercept, in theory, you would put 0 into the whole function. So you'd be like 0 over, you know, 0 plus 3 times 0 minus 3, and you would simplify that. But realistically, as soon as you have an x-intercept of 0, you know have a y-intercept of 0 as well, right? So those are the only intercepts we have. So it's not a terribly interesting function in that regard. And then what we're going to do is we've got our intercepts, and now we're going to look for our asymptotes. So I'm going to look for the asymptotes. So vertical asymptotes, they are going to be from the zeros of the denominator, right? So, you know, it could be like, oh, x plus 3 equals 0. So that means we're going to have a vertical asymptote at x equals -3, and x minus 3 equals 0. So that means we're going to have a vertical asymptote also at x equals 3. So we have two vertical asymptotes, -3 and 3. You don't really have to show it like this. I just think it's important that students understand, like, you know, you probably knew it was -3 by looking at it because someone told you like that. Anytime that you're in doubt, you can take a whole factor, right? This whole thing is a factor. you can set the factor equal to 0 and solve, right? And that is going to tell you what the root is, or the answer to that particular piece. So there they are. Horizontal asymptotes. If we look at the this function, right, this chunk right here, because that goes away, or I guess we could look at it over here. What we have is the numerator is a second degree function, and the denominator is a third degree function. That means that the bottom gets bigger faster than the top. So we're going to take a big number divided by a really big number. That's going to get close to 0. So the horizontal asymptote is at y equals 0. Okay. So yes, we've got a lot of details here. We would test behaviors on either side of our vertical asymptote, and I don't remember if I actually said that in the last thing. Again, behaviors near asymptotes is another thing that we would sort out again, but that's sort of an advanced functions thing, and we know how to do that. Recall, for those of you who don't remember, you can take the most simplified version of your function, which would be this right here, and if I was looking for behaviors near asymptotes, so maybe like end behaviors is always gonna, we're gonna sort those out, but maybe I'm just gonna say behaviors, and so we need the end behaviors. Now what's kind of cool about this one, behaviors, it's not having like that, behaviors is because it's a horizontal asymptote at 0, right? We do it again. And I'm going to sketch this better later on, obviously. But we have a horizontal asymptote at 0. Let's pretend that that's properly at 0. I know my end behavior has two choices. It can either come at it like this, or it can come at it like this. But regardless, it's got to get close to the 0. And similarly over here, it's got to do that, or it's got to do that. And there's different ways to test it. Probably the easiest way is to just take a large value of x and substitute it back into the the original function or your simplified function, so you could evaluate like what is f at -100, and because it's got to get close to 0, when you type that all in, it better end up being like 0.1 or -0.1. If you get like 15, I mean, if you get 15, be really skeptical that you've done it properly. Then test a bigger value. Test like f at -1000, and if it still doesn't go to 0, you know for sure that you've made a mistake. But you're going to test it, and you're going to find out that it's going to get closer to 0, either from above or from below. So this will always work, right? So this will work whether it's we're not going to do slant asymptotes, but we're going to do whether it's in case 1 or case 2, because imagine that we had a horizontal asymptote at y equals 3, you would know that the answer here should be like 2.9 or 3.01. And so this is a great strategy, but it's even simpler than that with this function, because we know the function after it simplifies a little bit is just going to be f at x is equal to 2x over x plus 3 times x minus 3, x plus 3 times x minus 3. And because the asymptote is at 0, we only really care if the end behavior ends up being positive or negative, because if it's positive, it's above, and if it's negative, it's below. So you can just kind of think, if I were to put in a large negative value, what would this end up being? So if I think about a large negative, so like -100, for instance, you can totally substitute it in and get the actual answer. But, I always try and emphasize how you can do it without a calculator. If you put that in there, -100 times 2, that's a negative value. -100 plus 3, that's a negative value. -100 minus 3, that's a negative value. A negative times a negative is a positive. A negative divided by a positive is a negative. So what we just found is that as x tends to -infinity, we've got that y tends to 0 from below. Now, this is not necessarily how we would want to state these behaviors. We would prefer to do it with limits. So in terms of limits, how we would state, this is the advanced functions way that we would have stated that behavior, but we're big kids now. So we're going to say the limit as x tends to -infinity of f at x, right? Because this is saying as I go to -infinity on this function, what is the result? Well, the result is 0 from below, okay? And we could do that exact same test with a positive large value. So, switch colors over here to be, imagine I want to do it for +100. it's going to be positive, positive, positive. So it's positive everywhere, right? And so it comes at it from above. So we know that it's going to go like this, and it's going to go like that, right? So you know, so the advanced functions method would be as x tends to infinity, we would say y tends to 0 from above. And if we were to do it with, and I want you to do it like this, the limit as x tends to infinity of f at x is equal to 0 from above. Okay, so we've got our end behaviors, right? So we have our end behaviors, and then again, depending on whose class you had, you should know how to test values on either side of vertical asymptotes. In a lot of cases, that can be done just using some good critical thinking, or it can be done by testing values on either side, right? So we have a vertical asymptote, wasn't it? No, it was at -3 and 3, right? So we have a vertical asymptote, so let me just get rid of that guy because I just drew in there so erroneously, at -3, and we've got another vertical asymptote at 3. And so we need to test on either side of that to establish whether, you know, it might go this direction or it might go this direction. Now, the reality is that you should already know what behavior is going on here, and you should all, like, I circled the right one, it will be that one. But you should know for sure on this side what's going on, and over here on this side what's going on. You should be able to figure that out by process of elimination. But just in case you can't, I'm just going to erase this piece. Sure, let's get a bigger one. In case you can't do that in your head or just with some critical thinking, what we're going to do is we can test, you know, I would test f at -3.1, and so that's going to be just to the left of this vertical asymptote. And again, I'm thinking about this same function, right? So I've got f at x is equal to 2x over x plus 3 times x minus 3. And I only really care whether the result ends up being positive or negative. So I think, okay, I've put -3.1 in the numerator, it's going to be a negative, over -3.1 plus 3 is negative, -3 minus 3 is negative, and so a negative times a negative is going to be a positive, and a negative divided by a positive is a negative. So we know that, as you know, as you know, advanced functions method, as x tends to -3 from the left, we just established that y tends to -infinity, and I'm okay with this notation here because this is sort of, it's flipped. It's not as x tends to infinity. Yeah. Well, okay. So I will take this. Given the times, I'll probably take that notation anytime. So if that's what you prefer, those of you going on to physics or engineering or computer science or math really should honor it's the limit as x tends to -3 from the left of f at x is going to be equal to -infinity, right? That's what we should really do. But okay, here's me committing. It's on recording now. I will accept the advanced function notation for behaviors near asymptotes if you want to do it like that. So then we would test f at -2.9, because that's going to be to the right, right? So I do the same thing. -2.9 times 2 is going to be negative over, well, the first one's going to be positive, and then it's going to be a negative. So a positive times a negative is a negative. Negative divided by a negative is a positive. So then we would say, oh, as x tends to 3 from the right, what we just, or -3, excuse me, from the right, we just established that y tends to positive infinity. Lovely. And then we're going to test f at 2.9, right? Because we need to test on, so we've tested on this one and we've tested on this one. Now I'm testing on this one. So f at 2.9 is going to be equal to, again, I'm only caring about positives and negatives. It's going to be positive over positive times a negative. Well, simplify that all, it's going to end up being negative infinity, not -1. So we would say then as x tends to 3 from the left, y is going to tend to -infinity. And then we could do the last one, and I'm just going to tell you it is going to end up being positive And so we would say as x tends to 3 from the right, we have that y is tending to positive infinity. Okay, so this is still all stuff that we knew how to do. Let's get into important points stuff now, because this is kind of where the rubber starts to hit the road. So I'm thinking important points. Important points. Okay, so I'm just going to write this function down again. And so we're going to have f at x is equal to 2x. And I'm going to go with the simplified version because it's going to ease my differentiation. Okay, so I'm going to differentiate that, right? I need the first and the second derivative. So let's go with just the first derivative to begin with. So I'm going to say f prime at x is equal to the derivative of the top, which is 2, times the bottom, which is x squared minus 9, minus the top, which is 2x, times the derivative of the bottom, which happens to be 2x, all over the bottom squared. So x squared minus 9 squared. Lovely. Good, good. And so, getting out of space. Okay, goes quickly. So this is going to then be, simplify that. So it's going to be 2x squared minus 18 minus 4x squared over this whole x squared minus 9 squared. Lovely. And so we can simplify that. And so it's going to be negative 2x squared minus 18 over x squared minus 9. Not the nicest derivative of all time, is it? All good. So I'm going to, what I'm going to do now is I'm going to let f prime at x equals 0 to find max mins. And this one is going to get a little bit interesting. So it's going to be 0 is equal to negative 2x squared minus 18 over x squared minus 9. Oh, forgot my squared there. Squared. And so basically, we can get rid of the denominator because I can multiply both sides. And then we can try and solve it. So I'm going to move that over, and we're going to get that 2x squared is equal to negative 18. Divide by 2, divide by 2. And we're going to get x squared equals negative 9. And I'm hopeful that when you look at that, you're like, therefore, there are no answers, right? Because I can't take the square root over the real number system of negative 9. So that means that, interestingly, therefore, there are no max mins. Okay, good. I'm going to then zip up to the top here, and we're going to continue on. Hello. Yep. Minimize this guy. Right, so we're on to a second derivative test now, which of course necessitates, oh wait, we actually have to do the first derivative test because we didn't actually do it. So this is where it's kind of interesting. For the first derivative test, remember, the tops, our t-tops, come from both vertical asymptotes need to be included and zeros of f prime at x. So in this case, there were no zeros of f prime at x, right? So we didn't have any of those. But we did have zeros, or we had vertical asymptotes, right? I don't have the dotted line handy, but it would be, oops, stop that, come back here. It would be good to make that dotted, but whatever. So negative 3 and 3. I'm going to label those as vertical asymptotes, right? Because they are. Duh. Oh no, I didn't even. Did I? I didn't even. No, we're good. We're good. We're good. Am I good? Yeah, we're good. Yeah. So on we go. And so I'm gonna get rid of those, right? Because vertical asymptotes are not allowed to play. Like, they're discontinuities by definition. They're discontinuities. So this is going to be from negative infinity to negative 3, and then from negative 3 to 3, and then from 3 to infinity. And I'm going to grab a test value, so like negative 5, 0, and 5. And then we would list it out the factors of the derivative, right? And so we had a negative 2x minus 18 was like the factors from the numerator and the denominator here. This is important. So we had negative 2x minus 2x squared minus 8, or negative 2x minus 18. Was it negative 2x squared? I gotta go back down. I can't remember. Yes, it is. It's negative 2x squared. Excellent. Okay, so back up we go. Negative 2x squared minus 18. And then the denominator, I'll include it. It was x squared minus 9 squared. Now, because this whole quantity is squared, we know that across the board, it's going to be positive, right? Because if it's squared, it's going to be positive. And then I'm going to think about result. And then I'm going to think about direction. So I didn't really make my sticks long enough. If I put negative in, it's going to get squared, and it'll be positive times a negative number, so it's going to end up being negative. I put 0 in, it's going to be negative. I put positive 5 in, it's also going to be negative. So the result on each one of these guys is negative, which means the direction is decreasing for everything. Oh, very exciting. Okay, so it's decreasing everywhere, other than where it's not defined. So yeah, so it's decreasing everywhere. Lovely. So there is sort of our first derivative. Let's consider our second derivative now. So our second derivative is going to end up looking like, so we're going to have, we had, so what was it? It was f at x, or f prime at x, excuse me, was equal to negative 2x squared minus 18, negative 2x squared minus 18 over x squared minus 9 squared. So you can see, like, I have to do this second derivative. They get big in a hurry, right? So yeah, so on we go. I have to do the second derivative. Here we go. So f double prime at x is going to be equal to the derivative of the top, which is negative 4x, times the bottom, which is x squared minus 9 squared, minus the top, which is negative 2x squared minus 18, times the derivative of the bottom. And this is a bottom that I'm going to have to do a chain rule on. So 2x squared minus 9 to the 1 times the derivative of what's going on here. So I have to chain it. So times 2x. And then that, goodness, my cats are going crazy. That whole thing is all over the bottom squared. So now we're going to have x squared minus 9 to the 4th. All right, so we've got some simplification and some greatest common factoring opportunities at hand here. So one thing, I don't want to do too many things at once. Okay, I'm going to pull out, I can see that I got an x squared minus 9 squared into the 1, so I can definitely pull out an x squared minus 9, right? And I've got a 2 times 2x is 4x, and a 4x, it's negative 4x, and I got a negative that I can pull there. So I can pull a negative 4x in common out as well, which really should be out front because it's just a monomial. So I'll do that. And so I'm going to pull out a negative 4x as well. And here we go. So the negative 4x, it's gone. One of the x squared minus 9s is gone. So that leaves me with one of the x squareds minus 9. So I'll just put it in like that. This 2 and this 2x, they went into our negative 4x. And this negative also went. So it now becomes a positive. And this x squared minus 9 is gone. And so the only thing I'm left with there is negative 2x squared minus 18. Lovely. Boop, boop, boop. All over x squared minus 9 to the 4th. This gets big in a hurry. Okay, now one of these guys can go with one of these guys, so it becomes cubed. So it's going to be negative 4x bracket. So we've got x squared minus 2x squared. So we have negative x squared, and negative 9 minus 18 is negative 27. Lovely. All over x squared minus 9 cubed. Okay. Lovely, lovely, lovely. I should simplify this. This is miserable. I have too many negatives up here, right? If I greatest common factor and -1 out of these two terms and bring it out front, then it'd be negative 4x. So I can make these all positive, okay? Which is just much nicer, right? Lovely. So here it is. Now I'm going to let f double prime at x equal 0 to find POIs, right? POIs. And again, I don't really need the denominator here, so it's going to be 0 is equal to 4x, and it's nice, it's already factored, x squared plus 27. And so either one of these can be 0, so 4x equals 0, which means x equals 0. Yay, there's one. And then we would have x squared plus 27 equals 0. Pop that over. We're going to get x squared equals -27, and we see that, and we're like, nope, there's nothing coming out of that. I can't take the square root of a negative number. So the only thing that's eligible to be a point of inflection is x equals 0, right? So now we're going to do our second derivative test. And again, I've mentioned, but I'll mention again, the second derivative test, it has not only all of the zeros from, okay, so I'm going to write this down. Second derivative test, the tops come from, again, vertical asymptotes come in there, and f double prime at x equals 0 solutions go in there. So we have 3 of them here, right? Because we still have plus and minus 3, right, from our vertical asymptotes. So -3, and then we've got 0, and then we've got 3. And this is a vertical asymptote, vertical asymptote as well. So I'm going to come down here and be like, regardless, these guys don't get to play. They are discontinuities. I'm not going to have room to graph this. So those are discontinuities. But this guy, it's f double prime at x equals 0. So it's actually eligible to play. So it's going to say -infinity to -3, -3 to 0, 0 to 3, and then 3 to infinity. Lovely. Test values, -5, -1, 1, 5 as an example. You could put just f double prime at x in here to do, like, we only care about what the sign is. Again, if you were calculatorless, I would advocate taking this and listing these all out independently, which is what I'm going to do. So I'm going to say this is, I got a 4x, I've got an x squared plus 27, I've got x squared minus 9 cubed, and I'm going to just pause this for a second, guys. And okay, so I'm going to substitute these values in, and again, I only care if it's positive or negative. This is going to be negative. Oh, this is interesting. X squared plus 27. Oh yeah, sorry, this is always going to be positive, right? I was kind of delusional there for a second. And this one, we're going to have to actually, pay attention to, because this one's always going to be positive, right? So I can just put positive, positive, positive again, because we're going to take whatever the number is and add a positive number to it. And so it's going to end up being positive plus positive. So those are all going to be positive. This one, we're going to have to be a little bit more careful, because we're going to have to evaluate what's going on inside the brackets. So -5 squared is 25 minus 9. That guy's going to be positive, because it's just going to cube, so no worries. I'm going to take -1. -1 squared is 1 minus 9. Hey, this guy's going to be negative, so that's important. And then we're going to take 1, and this guy's going to be negative, and we're going to take 5, and this guy's going to be back positive again. This is just going to match the sign of whatever I stick in it, and then we're going to look at results, right? So result. And so that's going to be negative, positive, negative, positive. And remember this, so here I'm going to not list direction, I'm going to list shape. Negative means it is concave down, it's a frowny. Positive is concave up. Good. So look, it changes concavity, but we have to be really careful. You might want to think, oh, that means that we're going to have a point of inflection. And this is why as soon as I put it down as a vertical asymptote, I'm like, no, it doesn't get to play. It's a discontinuity, so it is not a point of inflection, in spite of the fact that the concavity changes. So that's kind of two things to observe, is that A, don't say it's going to be a point of inflection, and B, this is the importance of including vertical asymptotes in our sign chart, because the concavity can, and in this case did, change on either side of the vertical asymptotes, which is really important. This one ended up being negative, so it is concave down, so it's frowny. And so, hey, this is actually defined. So what we have here is we actually have a point of inflection, right? And so we would substitute that in. The x value is 0, and then you would put 0 back into the very original function to find out your corresponding y value. But there's a root at 0, so I know it has to be 0. And then this guy is positive, so it's concave up, so it's happy. And again, it doesn't get to play, right, because it's a vertical asymptote, so it is not there. So we can now, and I've only got a tiny little bit of room here, but I don't feel like making a whole other sheet, so I'm going to try and do it right there. We can now actually graph with all of our details, right? So what I'll do to represent the vertical asymptotes is maybe make a really thin line. Can I do that there? Yeah, I think I can do that. So at -3, there's a vertical asymptote, and there's another vertical asymptote at +3, and then we've got a horizontal asymptote at 0. I can't even see that, even looking through my bifocals or not looking through my bifocals, but I know it's there. I know that we have, let me get my wider pen again. That's probably gonna be really wide. What color do we want to do? This color? Let's do this color. We had a root at 0. And then we can kind of assimilate all of this information. What we had is we had the end behaviors, right? So calculus didn't add a lot to this graph. We know that it's concave down, goes like this, and it approaches the asymptote. This is -3, this is 3. And then I know that it was concave up, and the end behaviors told me it did this, vert. And then this has some concavity to it as well, but it's decreasing everywhere, right? So concave, and then we've got our point of inflection right there. It's hard for me to draw this well with my tablet. And so this at 0, 0, this is a point of inflection. Now there's one piece, hopefully someone out there is jumping up and down. They know what I missed. I did it on purpose, believe it or not. We also had, and it's always ever so easy to forget, a removable discontinuity at, I think it was -5. Let me go look. I know we had one, but I don't remember where it was. I think it was -5. Yeah, at -5, right? So there is our function, right? And so that is the process. It is, unequivocally a long or relatively involved process, but that's what we need to do. So I am going to offer you some homework questions. So I'm going to say that your homework is going to be on page 213. 213, oh my goodness. That's not the right button either. Holy smokes. 213, number 4, D, G, and I. And you really should give those a work. Okay, thanks, children. Again, remember, even though I'm not with you, I am available. So, practice this stuff, take pictures of your questions, and I can hook you up with answers. Thanks, guys. Bye.